Is it angle and perpendicular bisectors?
No, it's only angle.
What makes you say so, Kate?
Because angles are angles and perpendicular means 90, and that's still an angle, so it's always an angle bisector.
How about this? Sure, we know that these are perpendicular, but perpendicular bisector means it does what?
It bisects a perpendicular, and it does not bisect it perpendicular. It's bisecting it at an angle, meaning it's not a perpendicular bisector.
Not quite. It means it bisects
The angle.
Well,
the side.
Nope.
And did they tell us that it's bisected?
No.
No, so we don't know that these are perpendicular bisectors. Sure, it's perpendicular, but we don't know that they're necessarily bisectors. But we do know that these are congruent, so that means that this is an angle
So it's an
bisector,
angle bisector.
and these are congruent, so that's an angle bisector. Do we see that there? That's the common mistake that people usually make in this unit, is assuming that it's one thing because we see it's perpendicular, but not realizing that it's the angle bisector. Alright, so for angle bisectors, where angle bisectors meet, what is that called?
The concurrence.
It is point of concurrency, and specifically for these it's
Circumcenter.
incenter.
So is an eye. Covering all their faces here.
So this is our incenter. And what do we know to be true about incenters?
They're the incenters.
They are the incenters.
So they're equal distance from each of the sides.
Very good. They're equidistant from both sides. So that tells me that those two little pieces are congruent, which is how you know to set 2x equal to x plus 3.
Wow.
I just guessed.
I did it.
I figured most of you probably just assumed, hey, there's only two equations to use here. They look about the same. Well, you need to make sure that you know your vocab inside and out. You have to know your vocab, and you have to be careful when you look at your picture, look at what information you actually do have to decide what you're dealing with here. Okay. Questions on that? Okay. So with that, then, what did we get for our answer for number 2?
5.
5? I think so. Yep, 5.
Yeah, I did that.
All right, how about number 3? Good, also 5. Number 4?
Focus it.
-1. -1? Are we allowed to have x equal -1?
Yeah.
And why? Correct. X itself is negative, but this whole, when we put it into our expression, the distance is actually positive. So it's okay to be a negative number as long as your length is positive. Okay. All right, how about number 5? What do we get? 5 halves.
That's unfair.
Why is 5 halves unfair?
It's not a full number.
Yeah, well, you can be 2.5. You can be 5 foot and 2.5 inches tall. So length.
No, but you wouldn't be. You'd be like 60-some inches. It's a sole number.
But you'd have a decimal, right? It'd be 62.5.
But doesn't the point of concurrency have to be 3 lines?
So Natalie asked a good question. So she said the point of concurrency doesn't have to be 3 lines. It is where all 3 angle bisectors intersect. But the point of in a triangle, all 3 angle bisectors always meet at the same point. So like the third one's going to go through that point as well. So the fact that they give us 2, that is the point of concurrency. The third one will always go through. So in a triangle, our angle bisectors always meet at a single point.
Apple.
And in a triangle, our perpendicular bisectors always meet at a single point. So if you have 2 of them, the third one's going to
PB, peanut butter and chocolate.
go. Peanut butter, veggies, and chocolate. Or chocolate and veggies, either one.
Peanut butter and
All right, what do we get for number 6?
ABI.
Good, 1 4. X equals 1 4.
I got 1 4 also.
Okay. All right, questions on any of these?
Yeah.
So again, we're dealing with we're dealing with angle bisectors. And if we were dealing with perpendicular bisectors, what would we have as our point of congruency? The circumcenter. And what do we know about our circumcenters? Same distance from what? Vertices. Vertices. Yes, so I know from my incenter it's equidistant from the sides. So from my incenter to the sides, those lines are right. They're all incenters of Okay, so with my incenter then, do I necessarily know that the distance from my incenter to my vertex is the same? No, we don't know that for certain. We only know for certain that the distance from your incenter to the side is the same. Okay, so see that difference? Okay, good. Alright, so let's take a look at our homework.
I forgot what veggies and spam.
Sorry, what? Oh, my fun acronym? I didn't have a good acronym for it. I just said if it was abs, it would be plural, so abs are, so one ab is. That's all I could come up with.
I like abyss.
Or abyss. Maybe you figure something out. Okay, so take a look at our homework. Sarah, you're up first. Number 1, what's the answer? They are congruent. Good. Number 2, Michelle.
X equals 10.
X equals 10. Number 3, Peter.
What's the homework?
Good. 50. Number 4, Sarah.
It was on the extra credit. Was that anonymous?
Can't tell you. People's work in the test.
I bet it was nothing that we would have.
No, because look.
Rob, what is the answer to number 4?
It wasn't long enough.
Good. LO equals 50. Number 5. Kate, what'd you get for 5?
5
Oh my
is
god, it was a bonus.
5 is a question.
5 is a question. From the information given, how is TV related to SU?
It's perpendicular.
Good, it's perpendicular. Grace, what's your question?
Oh, yeah.
Alright, number 6, Eric.
3.7.
Yes, 3.7. Number 7. Tiffany. 7.9, good. Number 8, Ian. Alright, number 9. It asks, according to the figure, how far is A from CD, and how far is it from CB? Remember, when we're talking about how far away it is, I want the shortest distance. And the shortest distance is the line perpendicular from the point to the line we're talking about. So number 9, Kayla, what'd you get?
15.
Good, 15 for both of them. Number 10, Eric. How is CA related to DC? Nope.
Wait,
We
number 10 now?
are on 10. Maybe if you weren't talking, we would know that.
Bisects BCD. I couldn't read my own words.
How do we know it's the angle bisector?
Because the DCA for the DCA.
And how do you know that?
I think the whole X thing.
The whole X
times
thing.
X, and
But
that's plugged in.
you would have to set them equal to each other, and you don't know they're equal. You have to first tell me how they're equal.
Well. CPCPC.
CBCTC, but we first need to show the triangles are congruent. Kate, how do we know that?
Because the hypotenuse on the right.
By hypotenuse laid. They share this side here. They share this.
Got it? He was just saying how it's not a
They share this, so
Guys, we're on recording.
it is congruent to itself. So we have the hypotenuse and we have a leg, which means that our corresponding pieces are congruent. All right, next up, number 11, Grace.
Is X 29?
Indeed, X is 29. Ivy, what'd you get for number 12? Good, 58. Number 13, Angelina.
measure of angle of BAC is 32 at BAC.
Good, they're both 32. Brandon, what'd you get for 14? Good. Number 15, Audrey. Yes. PR is the angle bisector of SPQ. How do we know that?
Side, side, side.
Yeah, we could use side, side, side. But then you could also use side, angle, side. Alright, number 16, Michelle. Michelle Trey. Number 17, Caitlin.
30.
Good, they are both 30. Number 18, Natalie.
BA equals 7. DA equals 7. X equals 2.
Good, X is 2, giving that our sides that they asked for are both 7. Alright, number 19, Chelsea.
X equals 5 and BEF equals 90.
Good. The angle is 90 degrees and X equals 5. Number 20, Liam.
X equals 6, BA equals 6.
Very good. Alright, questions on the front side? Alright, back side. 21. Nithya.
M is 7, and then LO and NO are both 14.
Good. 7 is M and our sides are 14. Timothy. Number 22.
X is 50 and QTS is 90.
Good. X is 15 and QTS is 90. Sarah, 23.
P3. There's a lot more of that.
P is 3.
I got it. Okay. IJ is 15 and KJ is 15.
Very good. 24, Michelle.
X equals 3, and I didn't get.
So X equals, or R equals 3. What is UW?
48.
Good, 48. Alright, 25, Peter. $25, Suraj.
5.
25.
Y equals 7 and D F equals 50.
Good, 7 and 50. Hey, number 26.
Yes. Promotion is right. Put a little star next to it.
Okay, give it a try.
So M equals 5.
Good.
And then, like, I got, like, 2P equals P. And I had no idea what it was.
Yeah.
Like,
Yeah.
So M is 5. What do we get for Peter? 10.
oh, never mind. I know I didn't.
Okay. Alright, now we're on to number 27, 28. So you have to decide if A is on the bisector of angle element. Remember, your angle bisector theorem tells us that any point that lies on your angle bisector is equidistant from the sides. Alright, so number 27, Eric. Is it an angle bisector? Or is it on an angle bisector?
I said there wasn't enough.
Okay.
Wait, I thought this like.
Good. So by hypotenuse leg, We then have, or because AM is reflexive to itself, it's hypotenuse leg, we know by CPCTC that these are congruent to each other. Also, the converse of the angle bisector theorem is true, that since these are congruent and perpendicular to the sides, we know it is on the angle bisector. All right, number 28, Eric, explain that one to me, yes or no?
28?
Yeah. No, it's not.
I feel like I got this one wrong though. Wait. Yeah, it's a bisector because it creates two congruent angles.
Yeah, they gave us the information stating that these are two congruent angles, so it's an angle bisector. All right, questions on those ones so far?
I feel really accomplished.
All right, so show me thumbs up, thumbs down, thumbs down, how you felt about the next four.
Actually, it's pretty easy.
Okay.
Oh, I can understand 30, 31, and 38.
All right, let's take a look at these together. My apologies for this printing. What?
That screwed me over.
Same thing.
That's really confusing.
Sorry. All right, number 29. First of all, what are we dealing with here?
We're dealing with perpendicular bisectors.
Good, perpendicular bisectors. And perpendicular bisectors all meet at a point of concurrency. Again, you need to know the vocabulary. What's your point of concurrency?
In circumvention.
Perpendicular bisector is what?
Circumcenter.
Circumcenter. I have her on this. So, alright, so perpendicular bisectors meet at your circumcenter, and what do we know to be true about circumcenters?
It's equal to the smaller vertex.
Good. So if G is my circumcenter, it is the same distance from each of my vertices, Ian, are you?
Oh, that's what that
Alright, so that means GB is going to be the same as GA, which is the same as GC. These have to be congruent because your circumcenter is equidistant from each of the vertices. Michelle, are you with me?
I'm with you.
Alright, so then what does that mean GA is? 12. They already gave us the distance for on the sides. We know that those are all congruent, so that's 12.
Where's the veggies?
Where's what?
The V.
Sorry. Is that what you wanted?
Yeah.
Okay. Equidistant from the vertices. Thus, we know those are the Alright. So then let's go ahead and tackle 31 while we're at it. So again, perpendicular bisectors. Point P is my circumcenter. And this is equidistant from each of my vertices.
GD equals that.
So PX equals
13.
13. Okay. Alright, now our other two problems, what are we dealing with? Angle bisectors. In angle bisectors, we have a different.
It means the side.
Well, actually, we're dealing with
What is our point of concurrency for
bisectors and
angle bisectors?
not.
You would do such an outrageous thing. It's breaking my heart. Like this. Yeah, maybe we shouldn't have been on it. Alright, angle bisectors intersect at the end centers. And our end centers are equidistant from what? The sides. So here are my angle bisectors. They are concurrent at the end center.
Yes.
And my end center is equidistant from my sides. So that means that GD is equal to. Yeah, I think there was a number in there that I just covered. Yes.
possible where it's like 3 words like where it's like same?
I think I want to say for an equilateral triangle, I think that might be the case, but I'm not positive. I'll have to double check on it. Okay, so 32.
You're better than this.
What is PM equal to for this one? 9. Now you're getting it. Alright. You should have your notes in front of you. Let's switch over to that. We've already learned about midsegments. We're going to just do a quick review of it right now before we learn about 2 new things. So our midsegment. What is a midsegment? You should know this from your vocab.
It bisects either side.
It bisects either side. It's a segment that joins the 2 midpoints, right? So segment that joins the midpoints of 2 sides of a triangle. Alright, so then what does our theorem tell us? What do we know about that midsegment?
It's parallel to the bottom.
It's parallel to the bottom, and we know one other thing.
Opposite sides are congruent.
Well, the opposite pieces here, or these pieces are
Half of the
congruent.
bottom.
But what?
Half of the bottom.
Good. It's 1/2 of that third side. So the midsegment is parallel to the third side. And it's half of its length. And is half of the length. Okay, so AC here is our midsegment. So if AC is my midsegment, it's the midsegment of triangle BED. So if AC is my midsegment, then we know that AC is parallel to ED, as well as AC is half the length of ED. So then AC is parallel to ED, and the measure of AC is 1/2 the measure of ED. We could also say that 2 times the measure of AC is equal to the measure of ED. You think of it that way too. Alright, questions on that? Let's move through these examples then. If AC equals 5 inches, ED is? 10 what?
Inches.
If measure BCA is 65 degrees, what is the measure of CDE?
130.
65 degrees.
Oh. Angle. Angle.
BCA. How do we know that that's true?
Isn't this like the same thing with corresponding angles?
Right, these are parallel, so that means our corresponding angles are congruent. Alright, AC is parallel to what? ED. Therefore, the angle BAC is congruent to the angle BED. And as we just said, this is because corresponding angles of parallel lines are congruent. Or you could just say corresponding angles postulate. Alright, so then if AC equals 2x plus 5, and ED equals 5x minus 20, Question is, what is x? Well, remember AC equals half of the long side ED. So AC equals 2x plus 5. 1/2 ED is 5x minus 20. Or you could have done it the other way, where you had 2AC equals ED. Thus you would have had 2 times 2x plus 5 equals 5x minus 20. Notice that would have been my next step, multiplying both sides by 2. So you can start off either way. Okay, when we do that, what do we get for x? Let's see. 4x plus 10 equals 5x minus 20. So x equals 30. Questions on that? Okay, so now finally some new stuff. So again, before we learned about perpendicular bisectors, and we learned that in a triangle, all perpendicular bisectors intersect at one single point of concurrency, which is called our circumcenter. Similarly, for angle bisectors, in a triangle, all of our angle bisectors intersect at one single point of concurrency called our incenter. Now, today we're going to learn about medians and altitudes, and guess what? They all intersect at one point of concurrency, and they each have specific names as well. Alright, so median of a triangle. From your vocab, what is the median of a triangle?
The middle.
Not just middle. Yes, it goes from your vertices to the midpoint of its opposite side. So a segment connecting a vertex and the midpoint of the opposite side. Alright, so just to draw a quick little sketch. There's your triangle. Midpoint's probably somewhere about here-ish. So my median would be from that angle there. So this here is a median. How many medians do we have in a triangle?
3.
3. How many perpendicular bisectors do we have in a triangle? How many angle bisectors? So again, just like our other ones, all the medians meet at one single point, and our point of concurrency of medians is called the centroid. You don't like that one. My favorite. Good, centroid. Now, something to note about centroids, they're always inside the triangle.
Always like that stuff.
I don't know.
I would look it up, but I don't have my phone.
Yeah,
It's
I can look it up
now.
later on your own time.
Oh.
All right. At this point, I want you to flip back to your notes from last class. I want to make mention of something. Lesson 1 notes. For perpendicular bisectors, we have circumcenters. And circumcenters, we talked about this briefly when we did our construction in Stinger, but we didn't formally write it down, so I want to make sure we write it down now. Our circumcenter can be inside, outside, or on the triangle. So I just want to make note of that. Can be inside.
What page are we on?
This is your notes from last class, lesson 1 notes.
Just go find it.
Can be inside, outside, or on the triangle. So the construction that I had up on the board, our circumcenter is actually outside. If we look at this triangle that's up here, my perpendicular bisector is here. Perpendicular bisector over here is probably about like that. Perpendicular bisector over here is probably about like that. So here my circumcenter is outside. So there's an example. Okay. So just know that circumcenters can be inside, outside, or on the triangle. Now, we stated this, but I don't think we wrote it down. On the back side, incenters, those are always inside your triangle. Okay, so incenters are always inside your triangle. Okay, questions on that? Okay, so let's go back to our notes. Okay, so our centroid is always inside the triangle, kind of similar to our incenter. And this next piece of information I think is really interesting. Does anybody know what else the centroid is known as or called? Center of gravity. Yeah. So it's also called the center of gravity.
What?
Oh, I'm so glad you asked.
Why?
I would have two-dimensional triangle at the center of gravity.
So it's the center of gravity of a triangle. And I'm so glad my favorite question was asked. Why?
Why? I don't like our
Because it's the point at which the triangular shape will balance. So it's called the center of gravity of a triangle.
Mine's called like the equilibrium of a triangle.
Why not the center of gravity?
Because if it's the center of balance, gravity doesn't well.
Because it's the point where a triangular shape will balance.
Spell because B-E-C-A-B-I-C.
Alright, so you guys are young.
That means triangles are weighted.
I mean, like,
You have an actual 2D triangle.
But even if it was weighted, it wouldn't be a gravity, it would be
Alright.
equilibrium.
So again, you guys are young, and it's the time when you guys start thinking each other are nice and you like them, and guys start wanting to impress the girls. So,
Talking about girls.
guys, I have a way for you to impress the girls now. Because it's clearly an impressive feat if you can balance 5 tortilla chips on your fingers at one time. So you can take tortilla chips, find the centroid of each one, and then balance them because you'll know the point.
That's not the center of gravity, that's equilibrium, that's equilibrium.
I haven't tried, but now I want to. I only have scoops at home. I need to go get tortilla chips now.
The balance would be
You gotta get the flat ones though. Flat.
equilibrium.
Oh, yeah.
Alright, so there you go, guys. Now you know how to impress a girl.
The center of gravity is like the center of the earth. It's like the center of
I know it's like today. The tortilla?
Okay,
gravity.
I have not tried it, but I just thought of it yesterday, so now I want to try it.
Equilibrium.
Alright, so just like we had perpendicular bisectors, your center of gravity, the closer is the floor, the more likely it is, or the easier it is to balance.
No, you
Yes,
do
Tiffany.
perfect.
I don't know, you can try balancing tortilla chips. Maybe I should say tortilla chips. The triangle ones. know, Angela.
I run away if it rolls through. If it rolls back into your chips, I'd run away. What the hell are you
Triangles have
doing?
a point concurrency to centroid, but it's not necessarily that all other shapes. So regular ones will intersect at the same point, but an irregular, like an irregular pentagon, their medians won't necessarily intersect at the same point. So regular ones. I don't know if that's still the same center. I would think so.
On the center of gravity.
Alright, so again, the point of concurrency for our medians is called the centroid. And just like our circumcenter had a nice, beautiful property about it, and our incenter had a wonderful property about it, our centroid has a wonderful property about it. And thus we are at our concurrency of medians theorem. Alright, the medians of a triangle. The medians of a triangle intersect at a point. And again, it is very important that you know your vocab inside and out this unit. So I'm going to make you write it again. What is the point at which they intersect? The centroid. Right, so the medians of a triangle intersect at a point called the centroid. And this part's really interesting. Our centroid is actually 2/3 of the distance of the whole median, 2/3 away from the vertex. So we'll write down and we'll take a look at what that means. So the medians of a triangle intersect in the centroid, or at a point called the centroid. That is 2/3 of the distance
So if you have the distance of the medians, you can find the distance of the perpendicular bisect.
You can find the distance from the centroid to the vertex, or even the centroid to the other side. Yes.
Why do people have to know, like, the medians of triangles and the distances?
So you can tell that it's centered with gravity.
So you can tell it's the center of gravity. So like if you're building like
Balanced triangle.
no, see if you're
So
building like
actually,
this
a triangle is like
tortilla
the
chip
most
and you want to
rigid
display
structure
it
to use.
and you want to put it on like a little point, you have to find the centroid to balance it on that little point that you made your giant tortilla chip on.
There you go.
Thank you, my question is completely answered.
Clearly.
For me to like.
Triangles are actually like one of the most rigid structures.
Wait, distance from each what?
I'd love to write it down.
Like, why don't we learn about the centroid and everything, or all these things about, like, different shapes? Like, why do you only do
Maybe some of them don't have centroids.
Because you only need to know for triangles because that's the most strongest shape in the world.
So
But a circle.
let me address all of that. So what I was telling Angelina earlier is that for a regular polygon, it'll meet in that same center. I'm pretty sure for all regular polygons it meets. But an irregular, like say an irregular pentagon, all the medians might not meet at one concurrent point.
No, it's like
The
this is
triangles
strongest.
are like one of
Circles,
the
like-
better structures, like rigid structures. So
Well,
it's probably
that's
why
already, like right. We already have that
focus
with
on
like
it.
right angles.
that's
Bisect, perpendicular bisect.
okay. So it's 2/3 of the distance
because
from each
diagonals,
vertex
when diagonals intersect each other, that's the center.
to the midpoint.
Median, then it's going from the vertex to the opposite. So it'd be like.
But that would make a
Of
triangle.
the opposite side.
Yeah,
Kate, are you with me?
I am very. We're talking about.
We're actually
That's good. But I want you also to keep up with this.
this paragraph. How do you find the centroid of a square?
You make a square and then make triangles in the square, then you find the centroid of a triangle.
It's the intersection of the diagonal.
Because the median's not. So what if you?
Oh, you know what?
A square
There's no
down
opposite
to the
side
middle,
for it.
I was
Why?
There's no
Yeah.
opposite
Why would
side
you
board.
pick that? You could have gone to the other side too.
Well, I guess that's the thing there. So I take back what I said about regular polygons. Because for a square,
Only ones with an odd number of
we don't have an opposite side board.
So what would you do for
So
like
take it back.
to go?
Well, pentagon is an opposite side.
No, but like.
Oh boy.
That was pretty good.
5 sides.
It doesn't have an opposite side. It's like one side. But where does that one side go?
Which one side?
The one on the bottom.
What?
Like what goes through there? What goes through there? Oh wait.
Oh, and it makes like a weird shape. Whoa.
Yes, it does.
That's so
Oh
cool.
wait, okay, you're right. Oh.
So let's go with odds. So odd ones that have the opposite sides. I don't know if that's technically still called a centroid or not. Point of ignorance. So
It's the center of gravity.
I think it probably is. It's kind of the exact center. Alright, so again guys, the things that we're dealing with right now are perpendicular bisectors, our angle bisectors, our medians, and if we can get to it, our altitudes. We're dealing with all these within a triangle. So these properties are all for within a triangle. So concurrency of medians within a triangle. Notice the medians of a triangle. So we're dealing with triangles. Okay, so what this is saying here. The medians of a triangle intersect at a point centroid. So here's our point. And that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So what this is saying is that if I take my median, well, each my median, so here's my median ES. 2/3 of the distance is PH.
Not okay with me.
1/3 of the distance is HS.
Why is this color red?
Yeah, why is it? Why was it red?
Because I told it to be red. Alright, so again, here's my median PS. PH
No, but
is
it's a red pen, so it works. Okay, I'm
PH is 2/3 of that distance. HS is 1/3 of that distance. Okay? So PH is equal to 2/3 of the entire median, PS.
Yes.
And thus the little guy, HS, is equal to 1/3 of the whole thing. So we have our entire median. The centroid is 2/3 of the distance away from your vertex, 1/3 of the distance away from your sector.
Oh, that's not fair.
2/3 of the distance away from your vertex, 1/3 of the distance away from your sector. Okay, so let's do this for our other ones. Alright, so QT. 2/3 of it is HT. So HT is equal to 2/3 of the whole thing.
So it's pretty much along the side.
The longer part of it, yes. The centroid is further away from your vertex than it is from the side.
I understand.
Peanut gallery in the back, are you with me?
QT doesn't look like a right angle.
And HQ is 1/3 of the whole.
I'm pretty positive QT is not a right angle.
It doesn't have to be. Medians come to the midpoint.
But I thought it was like.
So medians go from your vertex to the midpoint of the opposite side. It's not necessarily perpendicular. I'm glad you brought that up. So again, medians go from your vertex to the midpoint. It's not necessarily perpendicular. As you can see with the example we drew, it's certainly not perpendicular. It can be.
How is it?
It's
Said it could be.
not.
So for a right
So
triangle.
like,
It also looks like a bisector.
Well, it should be bisected, right? Because it's the midpoint.
Yeah.
I mean, of the angles.
Oh, so I'm glad you brought that up as well. So let's make sure we all understand this. My median meets the midpoint, so the other side should be in half. But it does not necessarily mean that your angle is bisected. These very well, and often are, two different measures. Also, it does not mean that it is perpendicular to the other side. It often is not. So your median only connects the vertex to the midpoint of the opposite side. Alright, so then our last piece, let's take a look at RU. Again, 2/3 of the distance is HR. So HR is equal to 2/3 of the whole thing. And the little guy, HU, is only 1/3. Alright, now that next part. We can think of it this way. Instead of saying pH is 2/3 of the whole thing, let's think about it this way. Alright, so going back to my first statement. pH is 2/3 of the whole thing, right? So this is 2/3 of my whole distance. And PS is just 1/3 of the whole distance. So this is 2 parts of the whole distance, this is 1 part of the whole distance. So would you agree with me that I could say that pH is twice the length of HS? Okay, so you can think of it that way. pH is twice the length of HS. Because it's 2/3 of the distance, 1/3 distance, this is twice the length. So likewise for our other ones. HT is twice of HQ. And likewise, HR is twice of HU. Questions on that? Okay, so then let's learn some actual numbers. If SP, this whole thing is 6 inches, how much is HS? 2 inches. What would HP be? 4 inches. Okay. Whole thing 6, 2/3 that. It's 4, 1/3 that's 2. Alright, but what if UR is 4 inches? If UR is 4 inches, how much is HR? So let's look at it. HR is 2/3 of the whole thing. Well, what's the whole thing? 4. And a reminder for those of you that have forgotten how to multiply fractions. Same thing as 4/1. We multiply straight across, which is 8/3. So then what would HU be? So HU is 1/3 of my distance, and 1/3 of the whole thing is 4/3. I mean, you can say 1 and 1/3, but don't you dare say a 1.3, because that's not correct. That'd be 1 3/10. All right, questions on this? Okay, flip it over to the back side. Almost there. All right, altitudes. Oh, sorry. Done? All right, so altitudes. So just think we had perpendicular bisectors that all intersected at one point, angle bisectors that all intersected at one point, and medians that all intersected at one point. We're now going to take a look at our altitudes. And what is an altitude?
I don't know what is an altitude.
You tell me. You should have done your vocab.
How actually do it? It's not my vocab.
Michelle?
The perpendicular segment that can measure is the vertex and the opposite.
Good. So it's the segment that goes from the vertex to the opposite side, but it's perpendicular. All right. So the perpendicular segment, the perpendicular segment from a vertex to the line containing the opposite side. The reason why we say to the line containing the opposite side rather than just the opposite side is because it's possible for it to be outside of the triangle. So our altitude can be inside, outside, or on, or even the whole side of the triangle. Okay? So let's draw rough sketches. Altitudes. Let's say there's a triangle. From this vertex perpendicular line, this is my altitude. Right, so it goes from the vertex to the opposite side and it's perpendicular. So notice the difference between medians and altitudes. Medians go from vertex to the midpoint. Altitudes go from vertex to wherever it's perpendicular. Again, we don't necessarily have that the angles are bisected. It's not necessarily the case. In fact, for this one, they're most certainly not bisected. Likewise, we don't have that it connects to the midpoint necessarily. In this one, it most certainly does not.
Where would the altitude go for like the left widest angle?
This one?
Yeah.
So it would probably be about. I think it would be.
It would be outside, right?
I think it would be outside. So whatever makes it perpendicular. So let's draw another example to display that, but hopefully this example makes it a little bit easier to see. What if our triangle looks like this? Okay. From this vertex, my altitude would be outside of it. Right? So that's what Caitlin was asking about. If I were to do the altitude over here, it would end up being outside.
What about the other?
But this one's a little bit more extreme.
The last.
This one here. I would say it'd be right on it.
On the left.
Oh, this one? This guy?
Yeah, it would be. No, yeah, wait.
I think that would also be outside. Yes, sir.
So if it's a right angle, then wouldn't like the altitude of the side be something?
You're so good. Alright, so then let's take a look at this.
Wait, so altitude's what? The highest point?
So altitude, we have an altitude for each vertex. It goes from each vertex to the opposite side.
Mm-hmm.
So we have 3 different altitudes.
Yeah.
So your altitude goes from the vertex to the opposite side and heads up perpendicularly.
Mm-hmm.
So then what Sarab just asked is, well, what if we have a right triangle? My altitude from this vertex would be the side itself. Oh, thanks, sir. So that's why it can be inside, as we see here. It can be outside, as we see here. Or it can be the side itself.
Wait, but
Each triangle will have 3 altitudes. Right now I'm just
Wait.
highlighting each different
So
one.
what if it's on, wait, so if it's on the bottom, it goes up?
You go from vertex to opposite side. So vertex to opposite side. From this vertex to the opposite side. From this vertex to the opposite side.
Oh.
So it goes from vertex to opposite side.
Wait. What would, see the second one easier? The vertex all the way to the left. That one, or would that go?
My guess is it would be it all.
Because yeah, the side would be that, and so we just go straight down. So
Okay, so again, just like we had 3 perpendicular bisectors, 3 angle bisectors, 3 medians, we also have 3 altitudes in a triangle. And guess what? For a triangle, all of our altitudes meet at a point of concurrency. And that is our concurrency of altitudes theorem. The lines that contain the altitudes of a triangle are concurrent. And guess what that point of concurrency is called? Orthocenter. It's my favorite.
I thought the other one was your favorite.
No, I really like that one, but orthocenter is my favorite one. I just like the one. Okay. And again, our orthocenters can be inside, on, or outside the triangle. So again, orthocenter is where they all meet at one point. And since my altitudes can be outside, in, or on, so can my orthocenters. Okay, so my first example here. My orthocenter is inside. This is an acute triangle. For all acute triangles, your orthocenter is inside. Let's say you look at our obtuse triangle next. Here, ABC is an obtuse triangle. We see our altitudes drawn here, and they all meet outside. So for obtuse triangles, your orthocenter is outside. And then finally, we have a right triangle. For a right triangle, from vertex X, there's my there's my altitude. From vertex B, my altitude. And from whatever vertex that was supposed to be Z. Start that out. They all meet on the triangle on that actual right angle. There's my orthocenter. So this is on the side. It's actually on. Okay, so you have all three. Now I included this little blurb from your book that just has a nice quick summary of each of the kinds that we learned. We have medians and altitudes is what we learned.
I like that.
Okay. Now again, we have review next class for your quest on Thursday. It is imperative that you are studying your vocabulary inside and out. I'm passing out your homework to you. It is both worksheet 2 and worksheet 3. Both of them.